So looking here at these things called parametric equations, we're recontextualizing the way that we approach relationships, at least in terms of these, equations, formulas, functions, that sort of thing, where up to this point, you're probably most used to thinking about these types of things, if not as functions, then at the very least as some sort of direct relationship, that a value theta begets a value r, or putting in something for x gets you out something in terms of y, or vice versa in either of those cases. That is, even if you don't have a clean input-output function, there is some kind of direct connection between one variable and the other, and they just go together as they are. And in a lot of cases that does do the job, and it does serve a useful and meaningful purpose. But it doesn't quite do everything. There are a lot of cases where we may be interested in seeing what other connections there may be, because it's entirely possible that even though there can be a relationship between x and y, like say if we have x equals y squared or y equals x squared, that one puts out the other as it were, it might be more meaningful to look at each of those in the context of something else. So for example, we're going to think in terms of the real world. We're going to think in terms of, summer vacation, because a lot of people are probably thinking about summer vacation right now. But let's say that as it's getting hotter, people want to go outside more, they want to go to the beach more. But when it's hot, people want to be able to enjoy themselves. So maybe they'll go to the store on the beach and they'll buy themselves some ice cream. So let's say that for every degree Fahrenheit it gets above 85 degrees, people will buy another ice cream sandwich from the local convenience store out there. It's a 7-Eleven or whatever. But also, some people are going to get out to the beach and they'll be concerned about their skin. They don't want to get sunburnt at the very least. So they'll probably be selling more sunscreen too. And let's say that for every degree above 85, they're also going to sell that amount of degrees squared bottles of sunscreen. So when it gets to be, say, 87 degrees, they're going to sell 2 ice cream sandwiches, and they will sell 2 squared or 4 bottles of sunscreen. Maybe not the most descriptively meaningful model, but it does make sense, right? That as it gets hotter, each of those things will go up. And then you might look at those 2 things going up and say to yourself, well, wait a minute. If for every degree there's another ice cream that gets sold, and for every degree there's that amount squared of bottles sold, would that mean that for every ice cream sandwich you get that amount squared bottles of sunscreen? That somehow sunscreen equals ice cream squared? Well, that's certainly a fun equation, probably more fun than a lot of what you're used to seeing from math, but, it's not the most meaningful relationship, is it? Besides being kind of a ridiculous notation to look at. And in this case, it makes more sense to recontextualize this and instead talk about each of those things as affected by the temperature. That is, sunscreen equals T squared, where T is the degree Fahrenheit above 85, and ice cream is just equal to T. Same T, though. Where, again, these two, they go together. They're driven by the same value. They're driven by the same parameter, as it were. But putting them into the context of one single equation wouldn't quite capture that subtlety. And that subtlety is the motivation for looking at these parametric equations, for which those 2 are kind of a silly example, but a meaningful one, nonetheless, for how these things work. That we look at a simultaneous relationship of some kind between 2 values, 2 variables, and an associated third variable, which we usually denote t, that drives both of them. Where when we get these, we call that value t, a parameter. And if we talk about graphing the collection here, we get what's called a plane curve, which is going to consist of the values x, y generated by those intervals of values t, where one of the 2 equations is driving the x value and one of the 2 equations is driving the y value. And usually we'll see these in such a way that t represents time, But t doesn't need to represent time. T can represent whatever we need it to be. But that's the most common one in applications, which is why I made sure to lead us off with one in here so you don't get the idea that we only ever parameterize for time. We can parameterize for anything as long as there's a meaningful relationship to be explored. And for our purposes, usually when we look at these problems, we're going to have that x is given by some function f of t, y is given by some function g of t, and we want to talk about graphing them. Where to do this, we have a pretty basic process where we select the values for t along the interval and usually pick the most obvious ones. We'll see what that means with an example. Then, for each value of t, we compute the associated x and y coordinates, and then we plot the points x, y, where we want to be sure to notate the direction of increase that happens for t along a smooth curve. And the next thing we're going to look at here is, again, just a quick example for how this comes together.